pre-cal, we're going to talk about polynomials, and in general, we're going to talk about how we can use some information we see right from the function to graph that. And this is kind of a two-day process. Today, we're going to talk about part of it. Tomorrow, we'll talk more about how to sketch those graphs. Some general information that we need to understand is that a graph of a polynomial could be what is called continuous, or it could be discontinuous. Continuous should make sense to you. What it means that there are no breaks, no holes, no gaps, smooth turns, no sharp curves are allowed. So basically it's just one continuous line. If you think about your pencil, it'd be your pencil wouldn't move too quickly in any direction or stop and be picked up, which is where discontinuous would happen. There would be breaks, holes, gaps, or there'd be a sharp curve, like in the case of a absolute value function where that v happens, that would be a sharp curve. This concept of continuous versus discontinuous becomes really important in calculus, so that's why we're kind of reviewing that real quickly. Also, when we look at a polynomial, we could talk about its degree. And a degree is the highest exponent. If it is of even degree, so to the second power, to the fourth power, to the sixth power, on and on and on, then both arms of the graph are either up or they are both down. They go in the same direction. And again, we're looking at the higher the exponent, the flatter the turn. So let's look at these three examples that I have for you. If we have x squared, like here, it's pretty thin here, this parent function, like you're used to seeing. If I go to x to the fourth, it's flatter here, and x to the sixth is even flatter. If you're not satisfied with those graphs, you could always put that into y equals of your calculator and test that to be true. But you'll notice that the arms of both of the graphs go in the same direction. If the polynomial has an odd degree, such as x to the third, x to the fifth, x to the seventh, like shown here, then one arm goes up and one goes down. In this case, we have all of them going from down to up because we're assuming that they're all positive and odd degree. Notice again that the higher the degree, the flatter the graph. So this one goes through pretty quickly. This one flattens a little bit. This one starts to flatten more. And again, you could check that in y equals of your calculator to make sure that you understand about that. So that's what we know about arms when they're even or odd degree. Now let's take a look at what the leading coefficient tells us. Let me get that into your view. The leading coefficient test tells us. Okay, we're going to look at the coefficient. Remember, coefficient just means number in front of. And if we're talking about the coefficient of the highest degree, we're talking about the coefficient of the number in front of the highest exponent's variable. If we look at the degree, we've already talked about if even or odd, what happens. Even means their arms stay together. Odd means their arms are separated. And then let's talk about positive and negative. If something is positive and even, then both arms go up like this. If it's even and negative, both arms go down like this. If it is odd and positive, we fall to the left and rise to the right. So it comes from down to up. If it's odd and negative, it rises left and falls right. So starts from up and goes to down. Let's look at an example of that. If we look here at example number 1, we have f of x equals negative x to the third plus 4x. And you can see the answer because I'm revealing it already to you right there. But in general, we can see that the highest degree is 3, so that would be an odd exponent. And it is negative coefficient. So negative and odd means it rises to the left and falls to the right. So that would be the answer. On your homework, I want you to show me both the words and the signs of what would happen. And that will probably be the same on the test. Again, this will be more useful tomorrow when you're actually looking at the graphs. Let's go ahead and look at another example. If we do f of x equals x to the fourth minus 5x squared plus 4, then what we're doing is we've got an even power, an even high degree of 4. The coefficient is positive 1, so it's positive and even, and we know that both arms then go up. Okay, so that's what we need to learn about leading coefficients. Part C for today is the zeros. Put that into your view. If I'm looking at what zeros mean, remember we've kind of already talked about this. A zero is just a place where the graph crosses on the x-axis or an x-intercept. If I'm looking at a function in factored form, so y equals and then all the factors, okay? If I plug in x equals a, if I plug in a here, then I would have a minus a, and that would be 0. So my zeros are at where x equals a, or where it makes this equal 0. My exponent of each of those terms is the k, all right, and that's going to tell us our multiplicity, which will be important here in a second. Okay, how does it cross? That's its multiplicity. So if this exponent has an even or an odd or a 1, that tells us about how it crosses the graph. Let's talk about those three ways. If k is even, such as x minus 3 squared or x minus 3 to the 4th, then it touches at A, meaning it doesn't actually cross, it just comes down and touches right here. And like we talked about on part A of our notes, how high this number is tells us how flat it is when it touches here. If it's pretty small, like 2, it touches and bounces back quickly. If it's 4, it flattens a little bit more. If it was 16, it would flatten a whole lot, but it still wouldn't cross. Okay, if k is odd, it flattens through the graph. For example, x minus 3 cubed might look like this. It crosses at the point 3 because 3 minus 3 is 0, and it goes through the graph, meaning it flattens through. The last type is if k equals 1, is a very special case. And if k equals 1, then it goes through at that point. So x minus 3 with no exponent or with the exponent of 1 crosses straight across like so. Let's do 2 examples to make sure we understand what this looks like when we're looking at a problem. The steps for how to do that are number 1, factor, number 2, find the zeros, and number 3, figure out the multiplicity. So if we look at example number 3, get that into your view, f of x equals negative 2x squared to the 4th plus 2x squared. And I want to factor that. What's in common here is the 2 and x squared. Because it starts out negative, I'm going to take the negative out. So my things I can factor out are negative 2x squared. And what remains is x squared minus 1. Okay, if I take that out. Remember to flip that sign if you take out a negative, if it started out positive. We also know that x squared minus 1 can be factored again because it's the difference of perfect squares. So I have negative 2x squared times x minus 1 times x plus 1. And now my polynomial is completely factored out. And I can start to look at the multiplicity. Okay, so to look at what the zeros are, I set each one of those pieces equal to 0, and I solve. On this one, I would divide by negative 2. 0 divided by negative 2 is 0. And then I would take the square root of 0, which is also 0. So it's x equals 0. On this one, it would be x equals 1 and x equals negative 1. I think most of you are pretty comfortable with doing that since we've been doing that for a little while now. Now if we look at the multiplicity, we want to know what is the highest exponent here. If this had another power, I would leave this in parentheses, and you could see that it's to the first right here. So the multiplicity here is 2, 1, and 1. Okay, so those are our multiplicities. Now go back to your chart that we just made about if k is even, odd, or 1. In this case, it is even multiplicity of 2, so it touches at that place on the graph. So at x equals 0, the graph touches the x-axis. At x equals 1, it crosses straight through because it's multiplicity of 1. And at negative 1, it crosses because of multiplicity 1. And so this right here would be my answer. X equals 0, multiplicity 2 touches. X equals 1, multiplicity 1 crosses. X equals negative 1, multiplicity 1 and crosses. That would be my full answer. Let's do one more like that. Example number 4, f of x equals 5x squared plus 15x plus 10. Here I can tell that I have some things in common that I could factor out. So I'm going to take a 5 out of each one of those pieces. And I'm left with x squared plus 3x plus 2. Once I have that trinomial, I know that that can be factored as well, and that's just part of knowing my factors. What multiplies to 2 and adds to get to 3, that'd be x plus 2 and x plus 1. And now I've got the fully factored form of the polynomial. I can now figure out my multiplicity and where it touches or crosses or flattens. If I set each one of my pieces equal to 0, starting with 5 equals 0, x plus 2 equals 0, and x plus 1 equals 0, I know that 5 will never equal 0. There's no variable to play with there, so there's nothing that can make that part equal 0. That one's out. On this one, it'd be x equals negative 2 and x equals negative 1. Multiplicity, if I go back to the factors, they're both of 1, so multiplicity 1, which means they both cross at that point on the graph. The assignment for this is A5, which is a worksheet. If you have questions, come to tutorials or let me know.